Welcome to Mythbusters.
This week on Mythbusters, we're going to be proving whether you can set something on fire without actually burning it.
So how are we going to solve the mystery of this myth, Peter?
Well, to go about this myth, first we're going to have to understand thermodynamics. To understand thermodynamics, first we have to go over the laws of thermodynamics.
Another important concept to thermodynamics is the concept of enthalpy, which is defined as the sum of the internal energy, E, of a system, and the product of the pressure and volume of the same system. Another important thermodynamic concept is entropy, which is equal to the heat transfer between the system and its surroundings divided by temperature. There is the Gibbs free energy law, which states that all the free energy in a system is equal to the change in enthalpy minus the product of change in entropy times absolute temperature.
So, to test this myth, we're going to have to run an experiment using money, a lighter, flammable liquid, and what we will do is we will have a control group where we just take the money and then set it on fire and see whether it gets burned or not. And then we will have an experimental group where we soak the money in a flammable liquid, rubbing alcohol, and then we set it on fire and see if it gets burned or not once it's aflame.
This is our control group. Test 1. Burning money. Seems to be burning, Pete.
That it does.
Now we're doing our experimental group, putting rubbing alcohol on the paper money.
As you can see, where there was rubbing alcohol, there is no burning.
As you can see from our two groups here, the bills on the left had rubbing alcohol poured on them and received no burn marks where the rubbing alcohol absorbed into the paper money. The bills on the right were not treated with the rubbing alcohol, and as you can see, the bills were burned or scorched near the tips.
From this experiment, we can conclude that our myth that you can set something on fire without actually burning it is plausible. This is all thanks to thermodynamics.
Thanks, thermodynamics. after doing that thermodynamic experiment, I think we should talk a little bit more about thermodynamics. For example, did you know that in the 19th century, thermodynamics was born when scientists were studying the steam engine?
That's pretty interesting. Did you also know that in thermodynamics they divide the universe into systems and surroundings?
You're right, that makes sense. Because in the first law of thermodynamics, it states that the energy of the universe is equal to the energy of the system plus the energy of its surroundings.
That's interesting. Did you know that to calculate the energy of a system, and from that equation, it's actually Q plus W?
You're right. That does make sense. The internal energy of the system is also made up of the kinetic and potential energies of the particles in that system.
That's a good point. Did you know that you can actually measure those energies with a calorimeter? This is an instrument commonly used in tandem with thermodynamics.
Speaking of all these kinetic and potential energies, don't forget about the law of conservation of energy, which states that energy can either be created or destroyed.
That's true. I wouldn't forget about that. That would also go along with the fact that you can't have continuous output from a machine after initial input. You need to have continuous input to have continuous output, which goes along with the law of conservation.
Oh, I almost forgot to mention, thermodynamics is the relationship, by definition, is the relationship between heat and work, which means it is a macroscopic theory.
Shh. It's just nothing. It's just nothing.
This is our control group, Burning Marnie. Alright, try again. Not dangerous at all. Wait. Aww. Dang it.
Oh.
That was too high.
Yeah, too ambitious. Oh, you had it going. Oh, oh God.
Whoa!